Alright, welcome back to particle physics and the standard model. This is lecture 41 and last time we saw why there were no FCNCs or flavor changing neutral currents in the standard model at tree level, right. When we rotated from the flavor basis to the mass basis of the Z boson interactions, we saw that indeed the rotation matrices in flavor space ate each other and you got an identity matrix. So, there was no CK matrix to talk about. We had already seen this explicitly in the Higgs-Yukawa interactions and it should be trivial to see this in the photon interactions as well. The key here is tree level, okay, because at loop level you can have flavor changing neutral currents in the standard model and that would make the rates of these processes like the decays that I have drawn here, but it is not just the decays, okay, even oscillations and scattering processes and so on. Anything that you can write with flavor changing neutral currents will always proceed at loop level, the vertex being provided by the flavor changing charged current with the W boson, right. So, because of this loop effect you are going to get very suppressed rates and that is the reason why we have not observed these charged current processes yet, okay. And from there on we moved on to the notion of having these flavor rotations in the lepton sector, right, and we saw that in the lepton sector you dumped all the rotations into the neutrino sector in particular. Why is that? Because neutrino flavors are easier to measure. It is easier to see the neutrinos in interaction basis than in the mass basis. We do not know the masses of the neutrinos, okay. We will see all that pretty soon, and also the fact that the converse is true for charged leptons. You know, when we discovered the electron, what we discovered was both the flavor basis and the mass basis at the same in the same shot, okay. Because electrons are not confined, they are easy to produce and detect and so on, charged leptons, okay. So, that is what we did and we got to the notion of a CK matrix equivalent which is called the PMNS matrix in the neutrino sector, okay. Once again when we rotated from the flavor basis to the mass basis, we could not help writing down a combination of rotation matrices. In this case, you know, you do not even need a combination because the charged leptons need not be rotated, but that the rotation matrix, flavor rotation matrix is nothing but the PMNS matrix, okay. So, that is what I have written down here. To be clear, I am going to rewrite it in a way that makes more visual sense, okay. This is the way it is generally written. You would write the flavor eigenstates in terms of the PMNS matrix itself. So, I have just rewritten this in this way, just remove the dagger, put the u on the other side, okay, or said differently, I hit both sides with a u. So, u dagger became unity, excellent, became the identity, okay. Now, once again I can parameterize the PMNS matrix in a way similar to the CK matrix with, let me quickly show you what I mean by that, you know, like this, okay, with 3 rotation matrices and once again a phase, okay. So, for this discussion we are going to only take one CKM phase, sorry, one CP violating phase. There are some models where you can have more than one CP violating phase. We are not going to talk about that, we are going to keep it simple here, okay. So, again let me not write that here, it is obvious, right, 3 rotation angles and 1 CP violating phase. So, using that parameterization as before, I now have oops theta 1 2 is 33.4 degrees plus or minus 0.7 degrees, that is the error. Theta 23 is 49.1 degrees plus or minus 1 degree. Theta 13 is 8.5 degrees plus or minus 0.1 degrees, and the CP violation phase, this is the funny bit. Look at the error bar here, it is 42 degrees on one side and 35 degrees on the other side for a central value of 197 degrees. Okay. So, these are as of November 2022. Okay. Why am I writing this? Because this is all an ongoing measurement. Okay. Notice a couple of things here. Remember again, when we parameterize the CK matrix, and I wrote this down, right, these are all small angles, right, 30 into 2.4.2, right. So, there were small rotations, correct, among the different flavors, but these are not particularly small, the first two are not particularly small, right, they are somewhat sizable, right. So, that means the neutrinos do mix a lot with each other actually, unlike the quarks. Okay, when you switch bases, then there is no way the new one, for example, is going to be completely like the, or mostly be the electron neutrino. The neutrino is not going to be mostly the muon neutrino. They are all nice admixtures of each other. Okay, that is one thing. By the way, there is a dot here. Okay. The other is, look at the CP violation, seems like a big angle, right, it seems like a big phase. Okay. First of all, even this phase, right, not enough to satisfy the Sakharov conditions. I must have talked about it in the very first few lectures when we talk about the matter antimatter asymmetry, right. I said you needed CP violation, one of the three conditions was you needed CP violation, right, in the early universe, but even this much turns out to be not enough to get the matter antimatter asymmetry we see on a universal scale. Okay. But that is not all, the error bars that I pointed out earlier, they are pretty huge, right. That is like a 20% error on the measurement that you are making, correct. So, that shows that CP violation is much harder to measure in the leptonic sector. Okay, that is all it means. It is very hard to manipulate and control neutrinos compared to quarks, even though they are confined. Okay. Okay. Now, I have not yet told you what PMNS stands for. CKM stood for Kabibo, Kobayashi and Maskawa, correct. So, PMNS, it is good to know the names of these physicists. It is Pontecorvo, Maki, Nakagawa and Sakata. So, you can see that in flavor rotations, Italians and Japanese have a monopoly over this, right. Okay, excellent. So, all of this leads us on to the notion of unitarity triangles. Okay. What is the unitarity here? The fact that we are claiming that the PMNS matrix and the CK matrix are unitary, right. Why unitary? because we are assuming that in flavor space you need unitary matrices to rotate from one basis to another, and we are asking what else could it be, right? It cannot be orthogonal because we are dealing with complex fields, and then if you want consistent rotations and diagonalizations and all that, you want it to be unitary, it has to be unitary, right? Nevertheless, this could be checked, okay? This is a very, very important check of the theory that we are writing down here, because these are all physically observable, physical observables, right? So, so a most important test is to construct what are known as unitarity triangles. So, where does a triangle come from? We will see, okay. So, as motivation, let me just write down helps test unitarity of the CK matrix, okay, in experiments. You can also do this for the PMNS matrix, it is just harder. So, we will just inspect the CK matrix, okay. First of all, what does unitarity mean? How would I write it? I know that I can write it this way, but in terms of the elements, how would I write it? I can write, do you agree, that if I actually carry out the multiplication of the matrices, this is what I have. Agreed? Right? Basically what have I done? I have taken the columns, I've taken the rows of the daggers and then multiplied it with the columns of the undaggered matrix, right? Or the other way around, you can do either way, both of them are allowed here. So, said differently, the rows and columns are orthonormal and only the diagonal elements are non-zero, in fact equal to unity, and that is what I have captured using the Dirac delta function, right. Sorry, it is not the Dirac delta, it is just the delta function, it is just a delta tensor, right. Okay. Now, what does this imply? So, let me write down one example of this sum, okay. Let us take VUD VUB star plus VCD VCB star plus VTD VTB star. Is this 1 or 0 according to this? Obviously, it is 0, correct. So, how many such sums add up to 0? So, unitary in this case it is a 3 by 3 unitary matrix. So, I have 1 1 1 0 0 0 0 0 0, right. That is what I get from here. So, I know that there are 6 such sums that add up to 0, correct. So, I am going to write plus 5 other vanishing sums, okay. All right. Now, what is this in the complex plane? Pause your video and think about this for a second. How would I represent this equation on a complex plane? That is exactly a triangle. Do you agree? I can exactly depict that as some triangle with this being VCD, VCB star, that being the length of it, right, on the organ plane, VTD, VCB star, right, VTB star, I am sorry, that term. So, this term is this, and then here of course I have VUD, VUB star. Do you agree? That is exactly what this is on the argon plane. Okay. So, this is what we mean by unitarity triangle. Okay. So, there are 6 unitarity triangles as we just saw, because there are 6 different sums, correct? Okay. Now, why is this important? Okay. This is where I am going to show you the picture that we have up here. So, this image is taken from CKM Fitter. It is an open source image. Okay. So, physicists have gotten together and contributed their experimental data, and the people at CKM Fitter basically take the data and fit it, get the best fit, do a statistical fit to obtain the best fit parameters, which they use to plot on this plane. Okay. So, what have they plotted here? Okay. They have literally plotted a unitarity triangle. Okay. They have literally plotted this, the triangle that I just drew here, right? That is exactly what they have plotted. That is why I chose these particular CKM elements carefully. Okay. This is the most popular one because that is the easiest to measure, alright. So, they have literally taken that, but you might notice that first, okay, let me first point out where the triangle is. See, that is the triangle, right. Okay. Now, you will notice that on this plane, you know, there are other variables like rho bar and eta bar and so on. So, what are those? That is nothing, okay, that is just a normalization. So, here I have taken VCD, VCB star, right. Suppose I set this to 1. In other words, suppose, you know, I just normalize everything to that particular element, then what would be the length of this? That is just VTD star, sorry, VTD, VTB star, okay, divided by VCD, VCB star. Okay. Why? Because I have literally normalized this to 1. Okay. And this is VUD, VUB star divided by that quantity VCD, VCB star. Okay. So, that is the normalization done. So, you use variables of you know, you just scale your variables to some rho bar and eta bar, that literally mean this. Okay. Now, how would you measure the unitarity using this? It turns out that you can measure the absolute values of these quantities, okay, up to the face. So, there is a so you know this angle, right, between these two sides of the triangle, right. In particle processes, often it turns out that you cannot really measure that angle. Okay. You can measure the CKM elements, the magnitude of the CKM elements. Okay. In that case, would you agree that if you can only measure the magnitude, you know, take this quantity, take these quantities, if you can measure all of these, then you know at best, since I do not know what the angle is, at best I can say that on the eta bar versus rho bar plane, I can be on this circle, right, going from here, taking that as a center, 1 comma 0 as a center, right. So, that is what they have drawn here. Now, you might wonder why are there bands? The bands just represent measurement uncertainties. Okay. But that is not all. If you can measure other CKM elements, again using particle processes, you take the correct mesons and the correct baryons so that they contain the correct quarks, okay, the B and the D quark and so on. So you measure with the best uncertainties possible the absolute value of the elements, but you cannot measure the angle. Okay, then what can you do? You can draw this circle. Okay, you can take this as the center of your circle, 0, 0, and you get this circle up to the measurement bands. Okay, so what is the use of this? Okay, I am going to remove the circles that I drew. The use is that it turns out, as you can see, that these two bands, right, they have literally shown this here, right, these two bands do intersect at this point, right. In fact, they seem to have drawn a little ellipse there, right. Can you see this little ellipse, that ellipse? So it shows that basically shows the best fit area where they merge. Okay, and the check is to see whether that best fit merging point does indeed correspond to the third side of the triangle. The triangle you can draw theoretically, right, but the question is whether the experimental measurements also match, correct. But notice it is not just that, there are other measurements also you can do. Okay, here they say epsilon k, right, I believe that corresponds to the kk bar oscillations. Okay, and data from that on this plane, can you follow the green band along here? So the data from that tells you that your eta bar and rho bar have to be along on this band somewhere. That is an independent measurement from these other measurements. Okay, but although it is independent, it also passes through this intersection point, right. By the way, in these circles you have actually two circles, there is an orange circle and a yellow circle, right. They too are again independent measurements, okay, and both of them again pass through that point. Okay, and look at the blue band here, okay, this whatever measurement that is, right. So the blue band that I am highlighting here, right, that also passes through this vertex of the triangle down here and the other vertex also, right. In other words, as you can see, all of these experiments, they all overlap at the right places, at the right vertices. Put differently, you do not have just one or two measurements to confirm that you do have unitarity. What you have done is, this is the technical term for it, you have over constrained, okay, this is an over constraining of the CKM parameters. Okay, and I think this is the most beautiful plot in particle physics. This amazingly illustrates the unitarity of the CK matrix, and hence this is a nice validation of everything we have been doing so far. Okay, it might have sounded crazy that we took a Higgs field, broke down electroweak symmetry spontaneously, and then got this flavor structure out of it by going from mass basis to from going from flavor basis to mass basis. All of this might have sounded somewhat abstract, but the proof is in the pudding, right. All these independent measurements clearly have over constrained the CKM parameters and proven over and over again that up to the measurement uncertainties, the unitarity of the CKM matrix is indeed true. It is not some abstract entity, right. So that is what this plot shows, and unitarity is indeed true. But there is yet another very beautiful use of constructing these unitarity matrices that I am going to talk about now. Okay, and that is the notion of CP violation in unitarity triangles. Okay, thus far we have not talked about CP violation really, right. We just took the three sides, whatever angles we got, it didn't matter, we check the unitarity, that is it, right. So, where does CP violation really come in here? Okay. So, to give a little background to this, remember way back when we were doing K0 K0 bar oscillations, right, I parameterized the CP violation with some epsilon, and then I said that is around 10 power minus 3 up to a factor of few, correct. And then, so this was CP violation parameter, right. And then now I switched to a different notion of CP violation, it's all the same, but it's just a different parameterization, and then I said there is a delta, right, in the quark sector, right, a delta CP, and then I said that was around 69 degrees, right, also CP violation, correct. So, this came in the CK matrix, right. See, these are all different parameterizations of CP violation, right, and this does not completely tell you how much CP violation there really actually is. 69 degrees does not really mean anything physically, right. 10 power minus 3, okay, it is like a fractional CP violation, it gives you some handle, but even that was parameter, the way I even that depended on the way I parameterized this epsilon k. Remember, we wrote two CP eigenstates, and then we said this is how we write the k long and the k short, right, and then suitably normalized it this way, right. So, even this depended on the parameterization that I used, and without the notion of k long and k short, where is this epsilon to talk about, right. So, what we would rather like to have is a basis independent, that is parameterization basis independent measure of CP violation, okay. That should be the goal. Then I have a clear way to express how much CP violation there is without having to recourse to these extra parameterizations, these extraneous parameterizations, okay. And I am going to tell you what that is, and then I am going to show you how to interpret this physically, okay. So, that is what I am going to wrap up this lecture with in the next few minutes, okay. First of all, I am going to tell you the name of this basis independent measure. It is called the Jarlskog invariant, okay. What is that? I am going to call it with a J. That is nothing but the imaginary part of so, I am slightly switching notation here, please do not get thrown off by it, okay. Instead of U, D and U, S and so on, I am going to use 1, 1, 1, 2 etc. Okay. So, these are still the CKM elements, okay. Every time I write a V, it is still a CKM element, okay. But it is not just this, it is also the minus of the imaginary part of V11, V32, V12 star, V31, but it is not just that also, it is also the imaginary part of, you see what I am doing here, can you see a pattern here? V32, okay, and so on, and there are totally 6 such combinations. They are all the same, that is why it is an invariant, okay. And in the next lecture we are going to see a physical interpretation of what this is, but now I am just going to write down what this is in the usual parameterization, okay. It is actually basis independent, but it helps to see what it is in one particular parameterization, the rotation angles and the CKM phase, right. So, in that parameterization with those 3 rotation matrices, this is what it is. So, cos 1 2, cos theta 2 3, cos theta 3 1, turns out there is a square just for this one, okay, and most importantly I am sorry, sine delta, okay. Why should there be a sine delta there? Because clearly delta goes to 0 would imply j also goes to 0, right. So, if there is no CKM phase, there is no Jarlskog invariant to talk about either, there is no basis independent CP violation either, okay. So, I will stop here. In the next class we will give a geometric interpretation to what this quantity is, and I will show you indeed that it is invariant, okay. And from there on we will go to neutrino oscillations. All right, thank you, see you in the next class.